So on Friday, we started graphing rational functions, rational fractional functions. And I like starting the way that I had you guys start it because it helps you to understand how we get that horizontal asymptote. So a rational function is a function of the form f of x equals, oh, I gave you guys something. I said n of x over d of x, where there's some sort of numerator, polynomial, maybe it's like 2x plus 3, so something in the top, and then some denominator, again, polynomial in terms of x, so maybe it's like 4x minus 7 or something like that. Where, n of x and d of x are polynomial functions, polynomial functions. And it's very, very important that we know that our denominator, d of x, denominator is not allowed to equal 0. We cannot divide by 0. And that's really, really important. One of the simplest rational functions is the reciprocal function, which is shown here. This is the reciprocal function. F of x equals 1 over x. All right, and that is the very most basic graph that we've talked about on Friday. Now, this rational fractional function has a vertical asymptote at x equals 0. It also has a horizontal asymptote of y equals 0. And again, we talked about that on Friday. So all rational functions, no, most rational functions, turn out to have those asymptotes as well, okay? However, as we found out on Friday, they can shift. So an asymptote is officially a line which the graph approaches. For example, in the graph to the right, the vertical asymptote. What is the vertical asymptote? Here's the vertical asymptote. -3. So x equals -3. The equation of a vertical line is x equals the number. And the horizontal asymptote is 1. And again, a horizontal line, y equals 1. All right. So this was x equals -3 and y equals 1 for our vertical and horizontal asymptotes. All right, and it's important to be able to see those and to recognize them when you see them. Now, I'm going to come back to holes here in just a second. Let's skip down to graphing. So, I do things in slightly different ways here, but one thing that we want to do is write the function in factored form. That is really, really important because it turns out we can see a ton of information when we see all the bubbles, okay? Now, on Friday, we talked about, well, how do we find that horizontal asymptote? The horizontal asymptote really answers the question, hey, we're looking at a fraction. So the question is, can you use long division? And that's sort of the answer here to figure out what you need to figure out. There are 3 different cases when we have a rational function. And the easiest case is what we started with, where the degree of the numerator is less than the degree of the denominator. The degree of the numerator is less than the degree of the denominator. That's something like, hey, maybe we've got like f of x equals like 2 over x plus 5, okay? The degree of the numerator is less than the degree of the denominator. That the denominator is a degree of 1. Anytime the degree of the numerator is less than the degree of the denominator, it turns out that we get a horizontal asymptote of y equals 0 all the time. And it's y equals 0 because I can't do any long division here. I wouldn't go, hey, can I do x plus 5? How many times does x plus 5 go into 2? Does that make sense? Doesn't make sense. We can't divide. It goes in 0 times. All right, so really it's asking the question, can we use long division? All right. If the degree is of the numerator is equal to the degree of the denominator, then again, we can use some long division and simplify it, but maybe there's an easier way. Okay. It turns out there's an easier way. If they're equal, so for instance, maybe you see something like 3x cubed plus yada, 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 over 2x cubed plus yada, yada, yada. So maybe your rational function looks something like this. The powers match, the degrees match on top and bottom. All right, well, it turns out in this case we could do some long division. And it would be, for our horizontal asymptote, 3 over 2. All we have to do is look at the leading terms. If they match, it's just the first two, the leading terms, all right? It reduces is all it does, which is kind of nice. So again, we could do long division if we wanted to, but it turns out it's simpler than that, okay? However, if the degree of the numerator is greater than the degree of the denominator, so maybe something like, for example, maybe we have 4x cubed plus yada yada over 2x minus 4. All right, this is a cubic on top, and we have an x to the first on the bottom. The degree on the top is bigger. Then we do need to do long division, all right? And we are going to get a slant asymptote, which we'll talk more about later. A-S-Y-M-P-T-O-T-E. All right, so there are 3 cases here, and I think today we're focusing on the first 2 here. So we're going to be graphing functions, and one thing I always start with is writing things in factored form, because it turns out in factored form we can see so many different things. So first, we can see a hole. A hole is a removable discontinuity. You can see the hole right here, or a break in the graph. And that happens when the numerator and denominator have a common bubble. They have something on top and bottom. All right? And so when they have something in common, that causes that little hole to happen. And we can see everything looking at that. Let's see. So here's how she says we should go through. Well, let me finish this, I guess. The function here, we have f of x. They factored it, and you can see we have this common factor of x minus 2 on top and bottom, which gives us a hole at x equals 2 anytime you have that common factor top and bottom. And what's the x minus 1 tell me? So actually, that's going to give me, if it's in the denominator, that's going to give me a vertical asymptote. Okay. If there's an extra factor on top, that's going to give me a 0. Hopefully, we'll see a bunch of these. All right, I'm going to show you how to do a lot of these things. We're going to just do some problems, though, because I think that's easier. I hate lists of information. I just don't think it's helpful, typically. So, turn the page. I want to look at number 3 to start. So I want to start here with number 3 so that you can see lots of different things that are happening. Always, 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 rule number 1 is factor first, if you can. Factor first, because I can see a ton of information when we're factored. Does the numerator factor? Yeah, it sure does. And let's see, x times x is x squared. What times what is negative 15? Positive 3 and negative 5. Beautiful. Okay. So when it's in factored form, I can see a ton of information. And first, right off the bat, I notice common bubbles on top and bottom. You'll notice how I circled them. I circled them because that tells me that that's a whole. A whole at -3. X equals -3. Now, then other bubbles, if it's in the numerator, I have a bubble left over. That actually turns out to be a 0. There's a 0 here, or an x-intercept, at 5, 0. So if it's on top, it's actually going to give me an x-intercept, which is kind of nice. All right, I want to show you one thing about the wholes here. We want to, if we were just simply simplifying, these bubbles would reduce, right? And what are we left with? X minus 5. If I want to figure out the actual location of the whole of a whole, what I'm going to do for that whole is, this is an X value. We know that we have a whole at -3 something. I want to figure out what that coordinate is so that I can plot it accurately, okay? So what we're going to do is very easily just take this value and plug it into the simplified function. So all I have to do is take -3 and plug it in place of the X there. -3 minus 5 gives me a -8. So it turns out that there's a whole at -3, -8. 1, 2, -3, 1, 2, 3, 4, 5, 6, 7. Right here is a itty bitty teeny tiny little hole. You're gonna need to know how to find that on Delta Math. You plug it into the simplified function. All right, so -3 minus 5. This function simplifies to x minus 5. That's just a line, isn't it? Yeah, it's a line with a hole. All right, graphically, it looks like this line, which of course goes through 1, 2, 3, 4, -5, and it has a slope of up 1 over 1, yeah. So it looks like a line, yeah, and it has a hole though. So we can always double check these, but again, the goal here is, can we figure these out? I'm going to go ahead, when you're doing this, I know you guys like to use the alpha F1 thing. I do not. When I graph stuff, I just put the whole numerator in parentheses and then the whole denominator in parentheses, just like that. All right, it's a numerator over a denominator. And so I'm going to go ahead and graph that so you can see. Does turn out to just be a line there, and I can trace and type in -3, and look at that. What's the y value? Nothing. It ain't there. It's a hole. It's not really there. It's undefined. All right. So there's a little hole in that graph, but that's what it looks like. It's kind of interesting. So let's look at number 4. What do you want to do first? Oh, I didn't do any of the rest of this stuff. Sorry, let's fill out the rest of this stuff. Denominator domain. That's a really big sigh. Denominator domain. What is x not allowed to be? X cannot equal -3. That comes right from the denominator. And we have a value that isn't here. What y value doesn't appear here? Yeah, so y turns out that it's not going to be -8. So I like finding all the stuff first. Our x-intercept is right here, 1, 2, 3, 4, 5, 0. The y-intercept right here, that's 0, negative 5. Well, there is no vertical asymptote in this case because it happens to be a hole, and there is no horizontal asymptote. Neat thing about rational functions is they're all a little different, which is kind of interesting. So let's look at number 4 again. What should we do first? Double if I can, yeah, which I can. Yeah, x plus 2 and x minus 2 over x minus 2. And we notice right off the bat, what do we have? A hole at positive 2. It always switches up, yeah. All right, so that hole traditionally would reduce, and so we get this simplified function x plus 2. That's just a simplified function. That's what it basically looks like, but we definitely have a hole. The x value is 2. How do we figure out the y value? Yeah, you just take that and plug it into the simplified function. So 2 plus 2 gives us 4. So there is a hole at 2, 4. And then go ahead and plot that, 2, 1, 2, 3, 4, and make a little, it's a hole, it's not really there. All right. The other bubble up top, what does that tell me? That's an x-intercept, yeah. X-intercept at negative 2, 0. Everything in bubble form we have to sort of solve, yeah? So there's an x-intercept at negative 2, 0. I can plot that. That's the actual point on my graph. Let's see. Other stuff. How do you find a y-intercept? We could just graph it. Like, this is easy to graph. We can always get a y-intercept by simply taking our function and plugging in a 0 for the x, which you can do in lots of different places. We can plug it in here at the beginning. If I plug in zeros at the beginning, I would have 0 squared minus 4 over 0 minus 2, which turns out to just be 2, and that shows right here as well. So we can see it in the simplified function as well, which is kind of interesting. So this is a y-intercept of 0, 2. But yeah, anytime you want to find a y-intercept, super easy to do. Just plug in zeros for x. All right, so let's see. I have a y-intercept of 0, 2. And then graphically, this is just a line, which has a y-intercept of 2. It goes up 1 over 1. So this is just a line, and it has a hole in it. Kind of interesting. What is the domain? Yeah, right here is the domain. Comes from the denominator. X is not allowed to equal 2. And the range? Yeah, we've got a hole, so that says y is not allowed to equal 4. So it's kind of interesting. And again, is there a vertical asymptote? None, yeah. And a horizontal asymptote, there is none in this particular case. All right, let's see. Do we have more that we can... Yeah, let's keep going. Turn the page. All right, number 5. So again, factor first. I can't do anything with the numerator, x minus 3, but the denominator double bubbles into... Okay, x minus 3, x minus 2. Good. All right. And so what do we see from our factored form here? A hole, yeah. So we have a hole at X equals 3. Okay, what's this bubble on the bottom? That's on the top. So again, denominator domain. Yes, this is going to give us a vertical asymptote at x equals 2. Vertical asymptotes and domain go all together. Same with holes. They're all part of domain. So vertical asymptote. So those bubbles are super nice. Let's see. So I know I have a vertical asymptote at x equals 2. I'm going to draw that in. Vertical asymptote at x equals 2. And I have a hole at 3. I guess I need to figure out my ordered pair for my hole. All right. So I know that my hole is at 3. How do we figure out what that y value is? Yeah, what do we plug that into? How do we... Yeah, if we were to simplify this, we'd have a 1 on top. These bubbles reduce to 1s, right? And then so it's over x minus 2 in the denominator. So I'm going to plug in that 3 right there. Yeah, so 1 over 3 minus 2. 1 over 3 minus 2 is just 1 over 1, which is 1. 1 over 3 minus 2, which is just 1. So I have a hole at 3, 1. 3, 1, I have a wee hole right there. Now, this is kind of interesting. This is a rational fractional function. So we're left with a rational fractional thing at the end. The others had cleaned up nicely to just a straight line. So here we have a rational fractional thing. So we're going to have a horizontal asymptote here. So here, the degree of the numerator is a 1. The degree of the denominator is a 2. Can we divide that? No, there is, you can't, it goes in 0 times. We can't use long division. Does x squared go into an x? No, it doesn't. It's too big. So the horizontal asymptote is y equals 0. And that's because this is that case where the numerator is less than the denominator. So I'm going to draw that. We got a horizontal asymptote at y equals 0. So that's the x-axis there. All right. Let's see. I want to go ahead and talk about the domain here. I have 2 things. The domain, denominator domain. So a hole and those vertical asymptotes. X cannot equal 2 and x cannot equal 3. So whatever comes from a hole or a vertical asymptote, anything in the denominator, that we can't have in our domain. What's not included in our range? Y. The y equals, y cannot equal 1, because that's where our hole is, the y value of 1. All right, let's see. I don't get any x-intercepts here because there's nothing on top I can set equal to 0. All right. What about a y-intercept? How do we find a y-intercept? Yeah, f of 0. And I can plug it in lots of different places. I can plug it in all the x's at the beginning, or I can plug it in at the end. Where do you want to plug in? The end? That seems a little easier, yeah? 0 minus 2. 1 over 0 minus 2. We get 1 over negative 2. Negative 1/2. So the y-intercept is 0, negative 1/2. Right there is the y-intercept. So to graph these, I know that a rational fractional function typically is at like L shape. So it's going to look something like this. Can we check this on our calculators? Yeah, absolutely. And again, I would, I just use parentheses around my numerator, and then x squared minus 5x plus 6, parentheses around the denominator. And we can check a lot of information here. Anything that has an x, we can check easily. So I can just hit trace and type in a 2, and you'll notice there's nothing for the y. That's because it's undefined. That's why it's a domain restriction. We're not allowed to equal it. I type in a 3. Again, there's nothing for the y. There's nothing there. It's undefined. If I have a 0 for x, I get a 1/2, a negative 1/2 there. My vertical asymptote is already undefined. I have the hole at 3. Well, I already checked that sort of, and it's nothing there. But if I go just to the right, there's Tinkerbell just to the right of that hole that was gone. All right. So anyway, so you can check lots. Let's do. Let's try 7, and then we're going to go back and do some of the easy ones. What do you want to do first? Double bubble, okay. Yeah, 2x minus 3, 2x plus 3. Ooh, what should we do in the denominator? Take out a 2 first. Yeah, I can take out the 2 first. There's a GCF there. And then I can double bubble. So if I take out the 2 and then double bubble, I get x plus 1, x minus 1. So look for a GCF, always a good plan. All right, do we have, oh, that's supposed to be a 1. X minus 1, x plus 1. Does this one have any holes? None. No holes. All right. Now, in the denominator domain, so all of these things that are in the denominator, those are going to give us domain issues, like our vertical asymptotes. So I have a vertical asymptote at x equals negative 1 and x equals positive 1. And those come right from our denominator. Vertical asymptote, x equals negative 1 and x equals positive 1. So we have these little dotted lines. It happens to match the domain. We're not allowed to equal negative 1 and positive 1. All right, what does the numerator bubbles tell me? Oh my goodness, there's so much, isn't there? Those are the x-intercepts on top, or zeros. So from these bubbles on top, if you take a bubble and solve it, what do you get? Yeah, 3 over 2. So we have 3 over 2, 0, and negative 3 over 2, 0. Those are the x-intercepts. So the top gives us the x-intercepts. The bottom gives us vertical asymptotes, or holes. So I have some x-intercepts, 3 over 2, 0, and negative 3 over 2, 0. Let's see, 3 over 2 is 1.5. So 1.50 and negative 1.50. Let's see, the other thing I'm missing is my horizontal asymptote. What's the case for this, our horizontal asymptote here? It is 2, you're right. So for the horizontal asymptote, I just look at the liters. Yeah, so the horizontal asymptote is 4x squared over 2x squared, which cleans up real nice to 4 over 2, which just reduces to a 2. So anytime the leading terms match, it's real easy to reduce them. So that horizontal asymptote is at y equals 2. And if I have a horizontal asymptote, that is something that my range is not allowed to equal. So they sort of go together. along with the holes. All right, let's see. I'm also missing my y-intercept. How do we find a y-intercept? Plug in 0 for x. Yeah, so f of 0. So I plug in a 0. I'm going to plug it in right at the start. Yeah, negative 9 over negative 2, which is just 9 over 2, 4.5. So my y-intercept is 0, 4.5. 0, 1, 2, 3, 4.5. Right there is my y-intercept. Well, this is really interesting. What do you think this one looks like? We have 3 points on the board. Kind of weird, right? Yes, very good. So all rational functions have some sort of L shapes to it. And that's going to be in these outer sections here. We have this sort of L shape that gets close to our vertical and horizontal asymptotes. And then, yeah, it's a parabola in the middle here, and it happens to be a parabola. But again, that's something you probably want to graph just to double check. You can always test points, do ordered pairs if you didn't have a calculator access or something like that. But, well, yeah, it's kind of interesting. All right. How are you doing with this so far? Can you be done? We've got to go back and do this first one. Turn backwards to number 1. Can we do any factoring? No, we cannot. So the top is going to give me my x-intercepts, and the bottom gives me my vertical asymptotes. And there's no holes here. So what is my x-intercept? Yeah, negative 1, 0. And my vertical asymptote is at x equals 5. Very good. All right. So my vertical asymptote is at x equals 5, and my x-intercept is at negative 1, 0. So I'm going to plot that, negative 1, 0, and I have my vertical asymptote at 5. 1, 2, 3, 4, 5. So 2 pieces of information. Oh, also, the domain and the vertical asymptote go together. X is not allowed to equal 5. What's the horizontal asymptote? The horizontal asymptote is 1. It comes from reducing. If they have the leading terms here, we just look at the leaders, and x divided by x is 1. So that's our horizontal asymptote, y equals 1. That's a horizontal asymptote, horizontal line. It also matches the range. Y is not allowed to equal 1. Everything else is good, but I can't equal 1. There's no holes here, no common bubbles. And the only other thing I'm missing here is the y-intercept. How do I find the y-intercept? Plug in a 0, f of 0. So 0 plus 1 over 0 minus 5, which would be? Negative 1 over 5. So my y-intercept is 0, negative 1/5. So 0, negative 1/5 is like right there. So is it a straight line? Graphically, this is weird because it's like a so it is all still rational fractional, so it's got to have the little L things. All right. So these L's go like this. Here's that bottom L, and the top L would be somewhere over here like that. Can you check it on your calculator? Yes. So today your goal is basically figuring out all these details. Where is the hole? What's the domain? What's the range? What's the asymptote? Okay. Do you have questions for me? Can you check many things using your calculator? Yes. All right. Oops.